Welcome to my YouTube channel, Ganesh here. Today I am going to discuss about two important terminologies we use in machine learning, data science and artificial intelligence. One is overfitting and the next term is underfitting. What is overfitting and underfitting? So before getting to these terms, let me talk about how a machine learning model works. So if you have a machine learning model, first you train the machine learning model with a training data set, that is labeled data set. After that you will use the testing data or unlabeled data to train this machine learning to test this machine learning model, and we will give predictions. So that's what we do in the case of a machine learning model. We give the machine learning model with training data, and we train this machine learning model, and after the training process we give the model with the testing data or unlabeled data, and we use it for predictions. So that's the simple concept behind this. And even we discussed about Arthur Samler, while he was working in IBM. It's in, I think it's in 1950. While he was working in IBM, he designed a program to play checkers. So what he understood is the program he designed is improving in the course of time. So that's what he coined the word machine learning. So that's what that already we discussed in the previous videos. So for the training of the machine learning model, we give training data. After that, for prediction, we use testing data. So all these aspects we discussed. Then what we need to understand here is two important terminologies. One is overfitting and another one is underfitting. See, this is the meaning. This is overfitting means it is giving a good performance on the training data. That is the meaning. Overfitting means it's giving a good performance on the training data and poor generalization to testing data. I already told what is training and testing. So it is giving a good performance if a model is giving a good performance on the training data and poor generalization or poor generalization. We call it as the variance. Poor generalization to testing data means it is giving a high variance. That is the meaning. So we will come to that point. So overfitting means good performance on the training data and poor generalization to the testing data. Underfitting means poor performance on the training data and poor generalization to testing data. That is underfitting. Here, if it is good performance on the training data and poor generalization to the testing data, it is overfitting. If it is poor performance on the training data and poor generalization to the testing data, it is underfitting. Okay, so we will get into the details more. See, to understand this, we discussed about data and what is this overfitting and underfitting. We already discussed. Now I will talk about two important terms we use in data science. One is bias, another one is variance. Bias and variance, two important terms we are using. One is bias and another one is variance. See, these two terms, if you talk about bias and variance, both are errors. See, from a machine learning point of view, both these terms are errors only. So what is an error for a machine learning model? It is the error coming in the prediction, right? So machine learning models we used for prediction. So the error means predicted value minus actual value. So what is an error? It is equal to predicted value minus actual. This is an error. This is for a machine learning model. This bias and variance are errors. Errors means predicted minus actual. Predicted value of a machine learning model minus the actual value. So these two terms, to understand these two terms more clearly, see first we discussed like we are giving the training data. For example, if you are giving a simple data set, see for example if we are giving height and weight to a machine learning model, see let's assume that we have the data like this. So very simpler form. You have the height here, you have the weight here. So you have height and weight. Height is this, corresponding weight is this, height is this, weight. So you have height and weight here is in centimeters, here it can be in kgs. So you have the table like this. So but in the real in practical applications, in real-time applications, you have billions and trillions of columns in the case of data. So here we just for our understanding we have these type of values here for height and weight. So we are training the machine learning model with the input data, with the training data set or labeled data set. After that, our model will give prediction for the height when we give the weight. So that's what, let us assume like that. So the model will give prediction for the height, for the weight. So we can plot a graph between these values. You have height and weight. So based on those values we can plot a graph. Here height is in the y-axis and weight is in the x-axis. You have height and you have weight. So when you plot these values, let us assume that you got one value here, 1 point here, 1 point here, 1 point here, 1 point here, sorry. So this is the plots, this is the points you got it. So we have the table, so before that by using this, let us assume that this is the points we got it. So we are coming up with a simple machine learning model. Let us assume that this is our model. So this model, when you see it's it is a linear regression, it is a straight line. It is denoted by the equation y is equal to mx plus c. Here y is the dependent variable and it is depending on the weight, and x is the independent variable, and m is the slope of this line. M is equal to tan theta, or in differential form in different calculus slope we will write it as dy by dx. Okay, so here m is the slope and c is the y-intercept. Y-intercept here it is 0. If you take a line like this, this is the y-intercept. Slope means this m means if you have this angle as theta, then the tangent of this angle, tan of you might have learned sine, cos, tan, trigonometric functions. Tan is equal to the formula opposite side by adjacent side. So the tangent of this angle we call it as the slope or gradient. Here m is the slope or gradient. Tangent of this angle is the slope, and c is the y-intercept. This distance we usually call it as the y-intercept, but here for this line the y-intercept is 0. So this is all about the equation of a line. Y is equal to mx plus c. M is the slope. Slope means the tangent of this angle. To find the slope of this line, you need to extend and you need to meet with the x-axis. Then you will calculate the tangent of this angle theta. and C is this y intercept, that is C. So you are clear, this is the this is related to linear regression. Okay, anyway, we are not getting into those details as of now. Now, so this is the model, machine learning. We came up with this machine learning model with a straight line. So what we can see is, see this line, this is the actual value. So this is our predicted value. So for this weight, see, this is the weight here. Our predicted value of height is this only, this much only. So this is the actual value, this is the actual plot. So this we can call it as the error. This is the error, right? So this is the, you can get it for a particular weight. See, for this weight we are trying to find out. So you have, these are all the points. These are all the points we plotted, and we come up with this model. So from our, see, we take a weight from this point, this is the weight, and the model predicts this is the height. This much is the height the model is predicting, but exactly the actual value is, this is the height. So this is the actual value minus this expected value. This actual value minus, the predicted value, that is known as the error. This error, we call it as a bias. So here it is having a very high bias. This model for each point, see, for here we have, this is the first point, this is the second point. You can see all these points. You can see from the graph the bias is more. So this, for this graph, the bias is more for all these points. Here you can see 1, 2, 3, 4, total 5 points are there. Here the bias or the error, the variation of the predicted value from the actual value is very high. So this model is having a very high bias. So we are coming up with another model. So this is the term related to high bias. So this model is having a very high bias, and we can call this model as underfitting. Underfitting. It is not fitting with the actual result. So this model is underfitting. Now we are coming up with a model which is fitting to this, it is, this testing, training data. So let us come up with another model like this. So this is a second or third degree equation. So this is a curve. So we came up with the next model which is a curve. This is a polynomial. Polynomial means the power can be 2, 3, 4. See, for example, if you take a parabola, its equation is y square is equal to 4ax. So it's a second degree equation. Or if you plot a third degree equation, you will get curves. So this is a curve. So you can tell this represents a polynomial, and this fits. See, it is passing through all the training data. So if you calculate the error here error is 0, because from this, for this weight, your actual height and the predicted height both are same. Error, it is 0. Here also error 0. Error is 0. Here also error is 0. Here also error is 0. Here also error is 0. That means the difference between the predicted value and the actual value is 0. Because it is this thing, we call it as this model, it is overfitting. It is overfitting. You understood? So this is having and this graph, it is having a low bias. So because the error is very low, so we can tell it as this polynomial. The curve, it is having a low bias. So this is having a low bias. This is having a low bias. The previous model, it's a linear regression model, it is having a very high bias, we call it as underfitting. So this is having a very low bias, but it is having overfitting. But the problem is, this is with respect to the training data. When we use these models for the testing data, what will happen? So now I am using this model to test. For it is a different data we are using for testing purpose. At that time, see this model, it won't, this is the plot of the testing data. So this is the plot for the testing data. So these are all the points we plotted for the testing data. At that time, we can see, even though this model was perfectly fit for the training data, for the testing data, it's giving error. So this error we call it as the variance. So this is another term. This is giving a high variance for the for the testing data. And for this also, it's giving a high variance. This is the actual value and this is the predicted value. For the training data, it's giving, and for here also, it is giving a high variance. So the variance is defined for the testing data, and bias is defined for the training data. So even though this model works perfect because it was overfitting for the testing data, training data, this model was perfect. It was overfitting for the training data. It's giving a very high variance for the testing data. So this is the variance, and if you see the other model, even the other model as well, we see it for the testing data, again it's giving a very high variance. So this model is having, it is for the testing data, again for the linear regression model, for the testing data it's giving a high variance. So when we talk about this linear regression model, it's having high bias and high variance, relatively high variance for the testing data. So this is what happens for the linear regression model. But for the polynomial, the curve, it is giving a low bias and high variance. So the linear regression model, we can tell it as it is underfitting, and the polynomial or the curve, it was overfitting. So that's the meaning. So the meaning is, what does it mean is like the overfitting means good performance on the training data. So overfitting means, this is the conclusion we can get it. Overfitting means good performance on the training data. Overfitting means good performance for training data and poor generalization to testing data. This is the case with overfitting. This is what means for overfitting. Now for underfitting, see what does it mean is, if it is underfitting, poor performance. If it is underfitting, poor performance for training data and poor generalization to testing data. If it is underfitting, poor performance for training data, poor generalization to testing data. If it is overfitting, good performance for training data and poor generalization to testing data. So we understood the terms, what is bias, what is variance, what is underfitting, see what is overfitting. So our machine learning, see one important point I can tell you here is our machine learning model, an ideal machine learning model must be having low bias and low variance, or it shouldn't be underfitting. It should come in between these two. So an ideal machine learning model must be having low bias and low variance. Here comes the bias and variance trade-off. So how do you optimize between these two? Because this bias and variance, they are inversely proportional. As one parameter increases, another decreases. How do we optimize these two things? So see, you have different methods. We will be covering these aspects in the coming videos. See, different methods are there. One is the ensembler method. You have boosting and bagging. Ensembler method for optimization. You have regularization. You have k nearest to neighbors. So a lot of methods are there to optimize between the bias and variance. One important method is the ensembler method, that is there only boosting and bagging coming into picture. So that's all about overfitting and underfitting. Thanks for watching.